Hello my friends and welcome back to the Today Machine channel. The bamboo paper production process at FOA is a testament to sustainable manufacturing and innovation. Situated in Shawan Lashan, the facility utilizes the healthy and green Neosynicalamus affini bamboo, cultivated across more than 6 million square meters of FSC-certified bamboo forests. The production process begins with the careful selection of raw bamboo, which is then fermented in a 400,000 square meter storage area after thorough cleaning and disinfection. This fermented bamboo is processed into bamboo pulp, forming the basis of paper products. The rapid growth of bamboo, combined with its natural antibacterial properties, ensures that these products are not only recyclable but also biodegradable. The facility integrates advanced technology into their production lines, allowing them to maintain stringent quality control. The company is among the first to be recognized as a dioxin emission reduction demonstration enterprise, ensuring that their production processes are safe and environmentally friendly. The factory, spanning over 330,000 square meters, is dedicated to creating a variety of bamboo paper products, including facial tissues, paper towels, toilet paper, and wipes. Each stage of production is carefully monitored, and all products undergo rigorous quality assurance before reaching the market. Through these processes, FOA produces bamboo paper that is both eco-friendly and safe for consumers, offering a sustainable alternative to traditional wood pulp and plastic products. When logs arrive at the woodyard, they are fed into a rotating drum to remove the bark. The logs are then chipped. The largest source of wood chips for papermaking is recycled offcuts from industrial sawmills. These wood chips are transported to the pulp mill on a conveyor belt. Upon entering the pulp mill, the wood chips are fed into a digester, where they are cooked in an acid solution to dissolve the lignin and separate the plant fibers. The pulp obtained from this process is termed wood-free, because the lignin has been dissolved. The fibers are washed to remove the acid solution, resulting in a soft and fibrous pulp. Before this pulp can be used to make white paper, it is bleached to remove any residual lignin, which would otherwise cause the paper to yellow with age. To protect the environment, this bleaching process is chlorine-free, using oxygen and peroxide. The originally yellow-brown wood chips are transformed into a soft white pulp, the principal raw ingredient for making paper. This treated pulp can be dried, baled, and transported to other paper mills that either do not have their own pulp mills or require specific types of pulp to impart particular characteristics to the paper. Whether produced on-site or purchased, the pulp is mixed with water at the paper mill. This pulp solution is refined by passing it through a series of rotating and stationary blades, which give the fibers a variable degree of clean-cut or fibrolated ends. Fibrolated fibers bind more tightly with adjacent fibers, creating stronger paper. Wood fibers alone would produce rough, textured, and unevenly dense paper, so fillers like calcium carbonate and clay are mixed in to increase opacity and control density. Dyes, optical brighteners, and sizes may also be blended into the pulp to enhance the paper's appearance. Water is a crucial material in this process. About 100 liters of fresh water are needed to make 1 kilogram of paper. Sophisticated wastewater treatment plants and closed water circulation systems on the paper line allow over 90% of this water to be recycled. The pulp solution, now a carefully controlled mix of fibers, fillers, and coloring agents suspended in water, is ready to enter the paper machine. The paper machine is the heart of the paper mill, a continuously running series of manufacturing processes that convert the pulp solution into the perfect paper grade for each market application. The head box, located at the beginning of the paper machine, injects the pulp solution at high pressure directly into the space between two continuously rotating wires. These wires carry the pulp into the gap former, which rapidly drains the excess water from both sides, immobilizing the pulp within milliseconds of leaving the head box. This turns it into a continuous web of paper, still wet and fragile but already exhibiting its most important sheet properties. The delicate paper web is then carried into the press section by continuously looped wet felts, which remove most of the water and prevent the sheet from tearing. At the shoe press, the paper web is forced between a soft rotating roller and a hydraulically actuated metal pad, squeezing out water, which is absorbed and carried away by the wet felts. The paper machine's longer section contains drying cylinders, huge heated rollers that dry the paper, giving it the strength to become self-supporting and ready for processes that will determine its surface qualities. The paper sheet passes along the machine at up to 1,400 meters per minute. Every process is continuously monitored to ensure manufacturing consistency. The paper passes through a machine calender, where two finely polished steel cylinders ensure consistent paper thickness. The paper then goes through a series of sizing and coating presses, where starch and coating colors are applied to its surface using a film press, enhancing its final appearance and qualities. Coating color is sprayed onto an elastic roll, which then transfers the coating film to the paper web through a process known as film press coating. This technique ensures a uniformly thick coating layer that closely follows the paper's surface contours. After each coating application, the paper surface undergoes drying through infrared heating panels and drying cylinders. This step is crucial for setting the surface with sizing, a process that encourages printing inks to dry on the paper's surface rather than being absorbed. As a result, this enhances the color intensity of the final print, while also improving the surface strength and water resistance of the paper. Once coated, the paper is wound onto a series of steel cores that press against a pope reel, ensuring the paper is wound at the correct tension onto each core. The paper line operates continuously, producing a jumbo reel every hour that contains 80 kilometers of paper, 8.5 meters in width, and weighing approximately 120 tons. Throughout this process, paper machine operators meticulously check the base paper quality, monitoring its thickness, opacity, and smoothness to meet exact specifications. Only when these parameters are confirmed to be within the desired range is the jumbo reel ready for further treatment and finishing processes. The final surface qualities of the paper are managed during the coating and finishing stages. The paper from the jumbo reel may be sold with different finishes, such as gloss or matte, and varying shades of white, whether natural or bright. The coating compounds are mixed according to precise recipes in specialized tanks within the coating kitchen. The primary color pigment used is calcium carbonate, which imparts a white surface to the paper. However, the coating solution may also include other materials like clay and talcum powder. Binders in the coating can range from natural starches to synthetic compounds, such as latex, which help create a smoother surface. To achieve the desired smoothness, up to 2 additional coatings per side are applied using the blade coating process. In this process, excess coating solution is sprayed directly onto the paper and then scraped off by a steel blade. The pressure exerted by the doctor blade determines the uniformity of the paper surface, smoothing out any irregularities. Each side of the paper is coated and dried in sequence to create the correct characteristics for each paper grade. At this stage, the paper has the necessary base characteristics and optimal coating consistency, but a perfect surface finish is yet to be achieved. The final surface finish is obtained in the supercalendaring process, where the paper passes through up to 10 rollers that apply pressure and temperature. These rollers have different surfaces, such as hard steel or soft rubber, depending on the desired gloss and surface treatment. As the paper is wound onto another steel core for transport, it now possesses all the required characteristics for its intended end use, except for one final step: sizing. The jumbo reels are then transported to a slitter winder, where rotary blades cut the reel into narrower reels, which are rewound and sent to the finishing department. Some of these reels are fed into a sheeter, which cuts the paper into sheets and stacks them onto pallets. Various printing processes, such as heat-set web offset, cut star, and label presses, utilize paper in reel form. These reels are moved forward on automated conveyor belts. Whether the paper is cut into sheets or remains in reel form, its final destination is the packing lines and warehouse. Each reel of paper is wrapped in craft cardboard to prevent damage during transport, and each pallet load of sheets is either shrink-wrapped or wrapped in protective rooms. Every consignment of both sheets and reels is labeled with a brand name, batch number, and destination, ensuring traceability of its manufacturing history. Finally, the paper, now a branded and quality-controlled product with precise characteristics, is ready for delivery to the customer. The introduction of the new €100 and €200 banknotes marked a significant milestone in the evolution of the euro currency. These banknotes, which are part of the Europa series, are designed with enhanced security features and a fresh design to better protect against counterfeiting while ensuring durability. The Europa series represents a significant step forward from the first series of euro banknotes, which were introduced in 2002. This article will explore the detailed process of printing the new €100 and €200 banknotes, their design elements, and the reasons behind the need for a new series of banknotes. The first series of euro banknotes. The first series of euro banknotes was introduced in 2002 when the euro became the official currency of the eurozone. This series comprised 7 denominations: €5, €10, €20, €50, €100, €200, and €500. Each banknote featured a unique design representing architectural styles from different periods in European history, known as the Ages and Styles theme. While the first series served its purpose for many years, advancements in printing technology and the constant threat of counterfeiting necessitated the development of a more secure and durable series. The Europa series. The Europa series, named after the figure from Greek mythology whose portrait appears on the banknotes, was introduced progressively in ascending order starting in 2013. The series consists of 6 denominations: €5, €10, €20, €50, €100, and €200. The €500 note was excluded from the series, as its issuance was discontinued in April 2019 due to concerns about its potential use in illegal activities. The new €100 and €200 banknotes were the last denominations to be introduced in the Europa series, entering circulation on May 28, 2019. These banknotes feature advanced security elements that are even more difficult to counterfeit than those in the first series. The design of the Europa series also incorporates a modernized version of the Ages and Styles theme, with more vibrant colors and rounded visual elements, making the banknotes easily distinguishable from their predecessors. Design elements of the €100 and €200 banknotes. The new €100 and €200 banknotes are packed with design and security features that enhance both their aesthetic appeal and their protection against counterfeiting. Architectural style. The €100 banknote features Baroque and Rococo architectural elements from 1600 to 1750, reflecting a period of grandeur and ornate design. The €200 banknote, on the other hand, depicts modern architecture, symbolizing the European Union's forward-looking nature. Map of Europe. The reverse side of the banknotes includes a map of Europe that now features Malta and Cyprus, 2 countries that joined the EU after the first series of banknotes was issued. Initials of the European Central Bank, ECB, reflecting the expansion of the European Union. The initials of the ECB are printed in 10 linguistic variants instead of the 5 used in the first series. This change was made to accommodate the languages of the countries that joined the EU in 2004, 2007, and 2013. Currency name. The word euro is printed in 3 alphabets: Latin, euro; Greek, EYP omega; and Cyrillic, EBPO. This inclusion underscores the linguistic diversity within the European Union. Signatures. The banknotes bear the signature of either the former ECB president Mario Draghi or the current president Christine Lagarde, depending on when the banknotes were printed. Both signatures are equally valid. Security features of the Europa series. To ensure the security of the euro currency, the new €100 and €200 banknotes include several cutting-edge features that make them extremely difficult to counterfeit. These features are the result of years of research and development and reflect the latest advancements in banknote printing technology. Raised print. The banknotes' front surfaces include short raised lines on the left and right edges, along with the main image, the lettering, and the large value numeral, all of which are printed in a thicker ink that can be felt when touched. This raised print provides a tactile element that helps people with visual impairments to identify the banknotes and adds an extra layer of security. Portrait watermark. When the banknote is held up to the light, a watermark of Europa's portrait, along with the value of the banknote, becomes visible. This feature is an essential part of the banknote's design, making it harder to replicate with photocopiers or scanners. Portrait window. One of the most innovative security features is the portrait window embedded in the hologram on the right side of the banknote. When the note is held against the light, the window becomes transparent and reveals a portrait of Europa that can be seen from both sides of the banknote. Emerald number. The shiny number in the bottom left corner of the banknote changes color from emerald green to deep blue when tilted. Additionally, the number displays an effect of light moving up and down. In the new €100 and €200 banknotes, tiny euro symbols are visible inside the number, adding another layer of complexity to the design. Portrait hologram. The hologram on the right side of the banknote, also known as the silvery stripe, reveals a portrait of Europa when tilted. The hologram also includes a copy of the main image and the value of the banknote, which shift and change as the note is tilted. Satellite hologram. Unique to the €100 and €200 banknotes, the satellite hologram is located at the top of the silvery stripe. When the banknote is tilted, tiny euro symbols move around the number, becoming more visible under direct light. This feature is particularly effective in making the banknotes difficult to counterfeit. The printing process. The printing of the new €100 and €200 banknotes is a highly sophisticated process that involves several stages to ensure the highest quality and security. The process begins with the design and selection of materials, followed by the actual printing and incorporation of security features. Design and material selection. The design of the banknotes is meticulously crafted to include both aesthetic elements and security features. The choice of materials is equally important, as the banknotes need to be durable yet retain a certain level of flexibility. Printing. The banknotes are printed using intaglio printing, a process that involves engraving the design onto a metal plate. The plate is then inked, and the excess ink is wiped off, leaving ink only in the engraved lines. The paper is then pressed onto the plate, transferring the ink to the banknote. This method produces the raised print that can be felt on the banknotes. Incorporation of security features. The security features, such as the holograms, watermarks, and raised print, are integrated during the printing process. These features require precise alignment and careful application to ensure that they function as intended. Quality control. After printing, each banknote undergoes rigorous quality control checks to ensure that it meets the ECB's strict standards. Banknotes that do not meet these standards are destroyed and recycled. Distribution. Once the banknotes pass quality control, they are distributed to national central banks within the Eurozone, from where they enter circulation. The recycling of paper at the Conyers Material Recovery Facility, MRF, is a detailed and efficient process designed to convert waste materials into valuable resources. Upon arrival, trucks are first weighed on a scale to document the amount of material they carry. Afterward, they proceed to unload their contents onto the facility floor. A front loader collects these mixed materials and deposits them into the in-feed bunker, where a drum feeder ensures a steady flow of material onto the first conveyor. Dust is managed using a mister as the conveyor transports the materials to the pre-sort line. Here, workers manually remove contaminants such as non-recyclable items, dropping them into designated bunkers below. Next, the materials move onto a disc screen. The screen separates cardboard from other materials, with cardboard climbing up the screen and the remaining items falling through. The cardboard then passes through 2 additional quality control checks before being manually loaded onto the baler line for compression into bales. The materials that fall through the disc screen are sent to a trommel, a rotating cylindrical screen that separates them into 3 streams: fines, medium-sized materials, smaller than 10 inches in diameter, and large items. The fines are conveyed past a cross-belt magnet to capture ferrous materials and an eddy current to capture aluminum. Large items are sent to a blower sorter, which separates light materials from heavy ones. Each stream is further refined on sort lines, where any remaining contaminants are removed. Light materials from the blower sorter are conveyed to the mixed paper truck, passing through a final quality control check. The heavy materials and medium-sized materials from the trommel are directed to the optical sort line. A ballistic sorter first separates two-dimensional materials from three-dimensional ones, with the two-dimensional stream processed to yield clean mixed paper, while the three-dimensional stream continues to the optical sort line. At the optical sort line, the combined feed is processed through a series of sorters and magnets, separating materials like HDPE, PET, and cartons. Remaining ferrous materials and aluminum are captured by additional magnets and an eddy current. Each separated commodity is directed to a bunker before being fed onto the baler conveyor, where it is compressed into bales. These bales are then stacked and loaded onto trailers for sale. The mixed paper stream is transported directly to the Pratt paper mill, where it is repulped and made into 100% recycled paper. This paper is either converted into new cardboard at an adjacent plant or shipped to other Pratt facilities, completing the recycling process. The extrusion process of a PVC window profile involves several critical stages to ensure the final product meets the required standards for strength, durability, and precision. The process begins with the PVC material being melted and forced through a die, which gives the profile its initial shape. As the molten PVC exits the extrusion die, it enters the tool exit stage. This stage is crucial as it directly impacts the profile's dimensional accuracy and surface quality. The tool exit must be carefully designed to minimize any deformation or irregularities that can occur as the profile transitions from the high-pressure environment inside the die to atmospheric pressure. The flow of the material must be smooth and controlled to avoid any stress concentrations that could lead to warping or other defects. Calibration. Immediately after the tool exit, the profile enters the calibration unit. This unit consists of a series of calibration tools or plates that are precisely aligned to maintain the profile's shape and dimensions. The calibration process is essential for ensuring that the profile meets the stringent tolerances required for window profiles. The tools are often cooled and can be adjusted to apply the necessary pressure to the profile, stabilizing its shape as it begins to solidify. This stage is critical in achieving the uniform wall thickness and sharp edges that are characteristic of high-quality PVC window profiles. Cooling. Following calibration, the profile moves through a cooling section, typically consisting of water baths or air cooling systems. The cooling stage is vital for setting the PVC profile's final shape and mechanical properties. The profile must be cooled evenly to prevent internal stresses, which could lead to warping or other defects. The rate of cooling must be carefully controlled. Too rapid cooling can cause brittleness, while too slow cooling can result in incomplete solidification. Extraction unit. Once sufficiently cooled, the profile passes through the extraction unit. This unit typically consists of a series of rollers or belts that pull the profile along the production line at a controlled speed. The extraction unit must be carefully synchronized with the extrusion rate to prevent stretching or compressing the profile, which can cause dimensional inaccuracies. This stage also ensures that the profile maintains consistent tension throughout the process, preventing any deformities. Assembly. After extrusion, the PVC profiles are ready for assembly into window frames. The profiles are cut to the required lengths, and additional operations such as welding, corner reinforcement, and glazing bead insertion are performed. The assembly process ensures that the profiles fit together seamlessly, providing a finished window product that meets the necessary aesthetic and functional requirements. Foaming and cutting machines play a crucial role in the production of foam products, particularly in ensuring precision, efficiency, and longevity of the equipment. A key component is the 3-conveyor continuous slab stock machine, which is designed for the continuous production of foam slabs. This machine integrates seamlessly with a panel board with touch screen control, allowing operators to manage and adjust the process with ease and accuracy. One of the core processes in this system is the liquid laydown process on a fall plate, where the foam's liquid components are evenly distributed, ensuring consistent quality and density throughout the slab. Once the foam is formed, it is cut to precise dimensions using a swing frame block cutoff. This system is known for its high precision, delivering consistently accurate cuts, which is essential for maintaining product standards. The swing frame design is another critical feature, specifically engineered to extend the life of the band knife used in cutting. This design reduces the stress and wear on the knife, ensuring a longer operational life and minimizing downtime for maintenance. For cutting foam blocks, especially those with low density, the carousel cutting machine is particularly effective. Operating at speeds of up to 7 RPM, it provides efficient and smooth cutting, which is essential for high-throughput production environments. Complementing this is the horizontal cutting machine, also designed for low-density foam, offering precise cuts while ensuring minimal waste. A special feature of these cutting machines is the tilting of the cutting frame, which further extends the life of the band knife by maintaining an optimal cutting angle. Additionally, the motorized pressure roller ensures consistent pressure during the cutting process, contributing to the overall precision and quality of the cuts. For specialized applications, such as pillow production, the pillow edge cutting machine is used. This machine is specifically designed for pillow edge radius cutting, providing smooth and accurate cuts that create the desired edge profile for pillows, enhancing their aesthetic and functional qualities. A sheet-fed offset press is a highly sophisticated machine used in the printing industry, consisting of 4 primary sections: the feeder and lay system, the printing units, the delivery system, and the control station. Each of these sections plays a crucial role in ensuring the precise and efficient production of printed materials. The process begins with the feeder and lay system, which is responsible for loading paper sheets into the press one by one from a stack. This system is designed to ensure that each sheet enters the press in exactly the same position, a critical requirement for maintaining consistent print quality. The feeder system utilizes air blast and suction devices to separate the sheets from the stack and feed them into the press. To prevent paper jams, double sheet detectors measure the thickness of each sheet, automatically stopping the feed if 2 sheets are stuck together. The paper is then aligned precisely by front and side lays, ensuring that each sheet is perfectly positioned for printing. The printing units are the heart of the offset press, with each unit printing a single color on one side of the paper. In a press with 10 print units, like the one described here, the first set of 5 units prints on one side of the sheet, while the second set prints on the reverse side, allowing both sides to be printed in a single pass. A perfecting cylinder between the 2 sets of units flips the sheet so that the reverse side faces upwards before entering the second set of units. The printing process relies on a series of color separation plates, each corresponding to a different color: black, cyan, magenta, and yellow in the case of 4-color printing. These plates must be loaded with extreme care to avoid any scratches, as even minor imperfections would be visible in the final printed image. Before the print run can begin, the plates are loaded onto the plate cylinders, which press against rubber blanket cylinders in each print unit. The print units are supplied with ink through a piped distribution system connected to a central ink reservoir. Modern printing inks are environmentally friendly, typically made from vegetable oils and biological solvents, in contrast to traditional inks that contained mineral oils. The press's software calculates the required amount of ink for each color based on the artwork, ensuring that the ink is distributed evenly across the rollers. Once the plates and ink are properly set up, the press is ready to start the print run. As the sheets move through the press, mechanical grippers pull each sheet into the first printing unit, where the printing process begins. The paper passes through each print unit, with the image gradually building as it moves through the press. After passing through all the print units, the gripper system pulls the sheets into the delivery section, where they are stacked. At this stage, the ink on the sheets is still wet, which could cause smudging or sticking if not handled carefully. To prevent this, an anti-set-off powder is sprayed onto the sheets before they are stacked. This powder reduces the risk of smudging and sticking, allowing the sheets to be handled and finished immediately after printing. Throughout the print run, the press operator plays a critical role in ensuring quality. An automatic scanner checks the registration and color saturation of the printed sheets, and although the plates are mounted accurately on register pins, fine adjustments may still be necessary to achieve perfect alignment. The press can automatically correct these adjustments, but the operator can also make manual adjustments via the control panel. The operator regularly takes sample sheets to confirm that the color and registration are correct, ensuring consistent quality throughout the print run. Once the printing is complete, the final stage involves collating the different printed sheets, binding them, and cutting them to size. The printed sheets are supplied in standard sizes and may need to be cut to the customer's specified dimensions using a guillotine. For products like books and magazines, the sheets are folded into signatures, sets of pages in the correct order but not yet cut or bound. A stitcher gatherer then assembles these signatures in sequence, adds a cover sheet, and stitches or staples the pages together before cutting them to the final size, resulting in a finished publication.